My name is Leroy Larry and welcome. Natural physics will explain in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as my astrophysics research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each. Greetings. My name is Leroy Larry, and welcome to Natural Physics, coming to you live from Costa Rica. In this episode, we will continue to use physics and mathematics to try to determine about how many human beings could it have taken and by what means to move our sphere. Now, on the subject of the weight of our sphere, I was very excited at the prospect that our sphere could be 100 tons. However, as I watched last week as that specially built tow truck inched its way 2 miles per hour through the streets of San Francisco on the way to the California Science Center, I thought to myself, the Endeavour space shuttle, I may have said San Francisco, I meant Los Angeles. I had a voice somewhere from the background telling me that I might have said San Francisco. Anyway, as I watched this tow truck transport the 85-ton shuttle, I thought to myself, is it really possible that our sphere is 15 more tons than the Endeavour space shuttle? Okay. As much as I got excited at the prospect that maybe I had discovered something new about our sphere, that it was 100 tons, I thought, Now, do you remember when I was talking about equations and I said that an equation is only good if it correctly describes what we perceive with our senses? Now, the equations that I used somehow caused me to arrive at a weight of our sphere of 100 tons. My perceptions, my common sense tells me that it's very hard to believe that our sphere weighs more than the Endeavour space shuttle. And I mean, watching that video just really emphasized that. So I determined to go back and look at my calculation to see if I had gone wrong. Now, remember where we started. Judging from my height compared to the sphere's height or diameter, we came up with the diameter of the sphere of about 1.8 meters. Half of that, 0.9 meters, which gives us the radius. And that's the key, the radius, to using some mathematical equations in geometry, as long as you have a spherical shape. And whoever he or she who built that sphere millennia ago, I'm giving them the benefit of the doubt that they have a perfect sphere. If you take into account the erosion of time and other natural factors, that's a sphere to me, okay? A thousands-year-old sphere. Okay, so the equations from geometry tell us that if we have the radius, we can get the circumference, which came out to be 6 meters. We can get the surface area, which came out to be 10 square meters. And most important of all, we could get the volume, which came out to be 3 cubic meters. I believe in the previous episode, I said 6 cubic meters, and I apologize for that. No, 3 cubic meters, which means that if you had 3 squares that were each 1 meter all the way around, 3 of those cubic meters would fit into our sphere. Now, this did not affect me coming out with the weight that I did. It had no effect. We'll find out what happened at the end. Okay, so we have the volume of our sphere. And the reason why that's so important is because there's an equation in physics that tells us that the density of an object is equal to the mass of that object with respect to its size, or mass over volume. So if we have we do a little algebra, right? So that we get mass on one side of the equation and density and volume on the other side. So what we have is that the density of the mass of our sphere is going to be equal to its density times its volume. We have its volume with the help of geometry, 3 cubic meters. Now the density. I looked up the density of gabbro rock, and it turns out to be on average 3 grams per cubic centimeter. And because we're working in the MKS system, meters, kilograms, seconds, we needed to convert that 3 grams per cubic centimeter to, it comes out to be 3,000 kilograms per cubic meter. So in each one of those 3 cubic meter blocks that will fit inside of our sphere, each one of those weighs 3,000 kilograms. That's packing. Okay. So what we came up with for our mass, oh, and by the way, the range that I saw about the density of gabbro rock, it ranged from about 2 to 3.5 or 2.5 to 3.5 grams per cubic centimeter. So I just took an average of 3 grams per cubic centimeter, which is 3,000 kilograms per cubic meter. Okay, so using that density and our volume, we came up with a mass for our sphere of 9,300 kilograms. And if you remember, I made it, because this is where I got into trouble. Remember, I made a distinction between mass and weight. The mass of an object is always going to be that amount. But depending upon where that object is, that's where the weight differs. On Earth, the mass of a particular object, it will have a certain weight. But if that object were to be on the moon, which is a smaller object than the Earth, the gravitational field is less, then the gravitational force on that mass is less, and therefore its weight is less. When you're in a swimming pool, the force of gravity on you is less because of the buoyancy of the water than when you're on dry land. So you weigh a little less in the water than you do on land, but the mass always stays the same. So we have our mass, 9,300 kilograms. Now, I brought gravity into the picture. Again, you have to be careful when you're talking about mass and weight. Your mass is your mass, your weight is the force of gravity acting upon your mass. So the simple way to have proceeded from then on, once I got my kilograms, my 9,300 kilogram mass, when you want to go from kilograms to pounds, 1 kilogram is about 2.2 pounds. So if we use that, we get, if we multiply 9,300 by 2.2 pounds, we get the value of our sphere in pounds, the weight of it. And I don't remember what that number is, but 1 ton is equal to 2,000 pounds. So when we divide the number that we got by multiplying 9,300 by 2.2 to get that amount in pounds, if we divide that by 2,000, we get a weight of our sphere of about 10 tons. A whole order of magnitude, right, lower than the 100 tons that I had excitedly thought we had come upon. So that makes a lot more sense. Although I'm a little disappointed that I hadn't discovered some, whoa, it's 100 tons, it's 10 tons, which makes a lot more sense, and it falls within the range of the weights that are given in the literature. So now that we are confident that we have a ballpark idea of the weight of our sphere, and again, remember, this was attained by not drilling down into it to get the radius, damaging a priceless artifact from the past. It wasn't gotten at by lifting it and putting it on a scale with or without the aid of the Incredible Hulk. We got the weight of our sphere by using physics and mathematical equations to at least give us a ballpark idea from which to start. There's the power, again, of equations. They're not mysterious. They're not incomprehensible. They're just a language that until somebody comes up with something better, it's what we have to try to describe the phenomena in nature all around us. Okay, so now that we have arrived at a reasonable weight of our sphere, what we're going to do in the next episode, we're going to go back to an equation in physics. The work that is done on an object is equal to the force applied to that object times the distance over which that force is applied. That makes sense, doesn't it? Simple equation: work is equal to force times distance. So basically, if you're carrying something that has a certain weight, okay, the work that you're doing is equal to the weight of that object, the force of gravity on it, making it heavy or light, and the distance that you have to transport that object. The work that the specially built tow truck did in transporting the Endeavour space shuttle from LAX, from the Los Angeles International Airport to the California Science Center, the total work is equal to the weight of the Endeavour, 85 tons, times the distance that the tow truck had to travel, which is 12 miles. So if we multiply the 85 tons of the sphere, which is the force of gravity on it, times the 12 miles that the tow truck had to travel, that's how much work that tow truck had to do in transporting the sphere. Now, it stopped at different points along the way for people to view it, to observe it. It actually took 2 days in total to go from the airport to the Science Center. And when it was moving, again, it was moving on an average of 2 miles per hour, but that was the total work. And again, remember, if we're going to multiply 85 tons by 12 miles to be consistent, you stay within the MKS system, meter, kilogram, second. Excuse me. So what that means is that we would have to convert the 85 tons to kilograms and the distance to meters to stay consistent. Now, again, in next episode, we're going to do that. And then what we're going to do is think about, okay, that's how much work would be required. But now that, but then what we're going to do is we're going to say, okay, now power is the amount of work that can be done with respect to time. So the physics equation for that is power is equal to work times time. And when you think about it, don't these equations make sense? I mean, even before somebody came up with the equation for work is equal to force times distance. Doesn't it make sense that the work that's required to do a task is going to be involving how heavy that object is in carrying it and how far you got to carry it? It just makes sense. The same thing with power. Doesn't it make sense that power would involve how fast you can work, right? Force times time. I hope I didn't say power is equal to work times time. No, power is equal to force times time. Work is equal to force times distance, okay? And again, doesn't it make sense? Power is how fast you can apply a force. How fast can that specially built tow truck carry the sphere from the airport to the science museum? Power. So next episode, what we'll do after we calculate the work that the shuttle did in transporting the sphere those 12 miles from the airport to the science center, we'll calculate the power that it needed to do that. And then we're going to attempt to say, okay, what would be the average power that an average human being, male or female, could exert in 1 meter or over in 1 second. We'll try to get an idea of the amount of work and power that would be required by an unknown and undetermined as yet number of human beings to move our sphere, let's say 1 meter, okay? And now remember, this is going to involve pushing it, where you have a serious amount of friction, or rolling it, which is going to be less friction. And again, there's physics equations that describe that phenomena. We perceive with our senses that it's going to be more friction to move that 10-ton sphere. Notice I didn't say 100. To move that 10-ton sphere by 1 meter, it's going to take a whole lot more force, a whole lot more work, a whole lot more power than to roll it. So perhaps using rotational physics, perhaps whoever is responsible for the spheres took that into account, maybe used rotational kinematics, rotational motion, as opposed to straight line. These are some of the things we will look at. Now, I have to let you in on something. We had such an awesome demonstration planned for you. Mariella, who's up in Guanacaste, had put together a live demonstration on the beach up there, where there's a lot of magnificent boulders. And she was going to demonstrate just how difficult it is with a rock on another rock to form any kind of shape, let alone a sphere. Okay. Now I know the spheres are made of different materials. Gabbro is one. I believe it's stated that some of them actually in the interior have a crystalline structure. Now, I don't mean that they have crystals inside, more that their atomic structure is crystalline, which, by the way, and which we will talk about down the line in futuristic physics. When you start talking about crystalline atomic structure, you get into what's called crystal technology. And that involves how atoms and molecules vibrate when they receive energy from a laser or some other energy source input. And it's right on the fringes of advanced physics. And the fact that some of these spheres contain that type of atomic structure in their interior, there's definitely room to talk about the implications of such. So, and then of course, we will also talk about the ancient aspect of these spheres. And what we must not lose sight of is that only this area of Costa Rica is where these spheres were constructed. Was there some attribute of this area, magnetic field, energy, potential energy, thermal, that made the construction of that aided in the construction of these spheres. I mean, there's just so many things that we can look at. And again, we will look at this through the lens of physics and mathematics and determine the plausibility of some of the ideas that have been put forth or that we may even come up with. But Mariella was going to demonstrate first how difficult it is to use rock on rock to form a sphere. And then she was going to demonstrate how even nature can't do that. Water is one of the most powerful forces, natural forces, right? I mean, a single drop of water dripping on a rock granite hard surface, if it does that over millennia of years, it will form a hole in that solid rock. That's the power of water. The Grand Canyon in the United States was carved out by the flow of that river over millennia and millennia of years. Now, on that subject of forming stone, and we'll talk about this more in our ancient aspect of when we look at the spheres. I came across an obscure article years back. I'll really have to search to find out where I came upon it, but it basically was from the log of an exploration that went into the depths of the Amazon jungle. And I believe it was turn of the century, late 1800s, early 1900s, something like that. And so as this expedition came upon a clearing, the leader of the expedition noticed that, okay, there was this sheer granite cliff in the distance. And he observed birds perching in their nests in the sheer face of that cliff. And he made just off the cuff comment, wow, lucky for the birds that those little holes are already in the cliff for the birds to use as their nest. The indigenous person guide told him, oh no, the birds made those holes. And he said, what do you mean? The guide told him, okay, just watch a little bit. And he did. He noticed that some of the birds were traveling back and forth into the jungle. And when they would return, they would have a reddish brown leaf in their beaks. And they would perch on the side of this sheer granite cliff and rub the leaf with their beaks on the side of this rock. And then they would take off and go back into the jungle and come back repeatedly, multiple times, right? And then after a while, they would perch on the spot where they had been rubbing and would start to peck that spot. And pieces of the solid granite rock would break off. This is in the log of this, I don't know what country the expedition was from, Europe, what country in Europe, but this is entered in this person's log. So here you have the possibility of a plant that existed, hopefully still exists, that when broken up and made into or just broken up, made into a kind of a solvent, is enough to soften solid granite. Now, if, let's say this exists, and let's say the indigenous peoples had knowledge of this plant, think about it. The blocks of Machu Picchu that fit so perfectly close together, the stones that were made, on average 2.5 tons block stones that were used to make the Great Pyramid, how perfectly they fit together. You can't even put a razor blade between these blocks. Machu Picchu, the blocks are all kind of shapes, not just square, rectangular. You got trapezoids, octagonals. I mean, you just like as if just, oh, here, it'll go there, boom. Oh, it'll go there, boom, right? Just now how? What if these people knew of this plant that if you ground it up, made it liquefied it, and you put it as a paste on the surface of one rock, right? And then on top of that rock, you put another rock and you just let gravity do the work, right? You've pasted, maybe you'll paste the surface of the one that you're going to put down. But point is, you put this liquid solution of vegetable plant that softens solid rock, and you put another huge, immense block on top of it. Oh, gravity's just going to go, woof, right? And you have an airtight contact that cannot, that is, I mean, you just can't even put a sheet of paper between it. So this points to the ancient knowledge that definitely ancient peoples had, that definitely has been forgotten or lost. They knew how to work with the earth, with nature. And this show, Natural Physics, part of it is about reconnecting with that knowledge. So I will leave you with that story. And again, with the sphere here, now that we have determined a more reasonable, correct weight for it, we are going to proceed to look at the human capabilities that existed millennia ago that could have been responsible for moving it. The question of how, Mariella will have a chance to do her demonstration next week. It's a beautiful demonstration. It's on the beach, the waves, the ocean. I mean, I imagine millennia ago, an indigenous person walking along this same beach and looking for that perfect boulder, right? That perfect rock. Oh, that's gonna be my sphere. I may be spending my next 30 years to chisel it, but it's gonna be my sphere. Again, it just boggles your mind at how and why. Who and when, they're mysteries too. And hopefully we'll get a chance to ask that question later on to an elder in the Bree and or Baruka tribe. We definitely are hoping for. So stick with us and tune in next week. Same fat time, same fat channel.